Thanks. Whoa. Move that away a little bit. Okay. I'm going to talk today about chemistry of reef aquaria, obviously. And in putting together a talk like this, it's sometimes a little hard to decide what exactly to talk about, how much detail to put in. I'm sure there's some of you out there that are going to know everything I'm going to talk about. And I'm sure there's some of you that it's almost all going to be new. So just try to bear with it. It'll move back and forth between different levels of things. I'm going to try to squeeze in a lot of things today. If it starts to run late, I'll squish them down at the end, so we won't talk so much about the ones at the end if time starts to run short. But the first thing I'm going to do is run through a couple of slides that talk about everything in a reef aquarium. But then I'm going to focus really on calcium and alkalinity and pH. If you look at the online forums, there's no question that's the biggest chemistry problem people have by far. They're also kind of hard problems to solve sometimes. Then there's a whole host of other problems that people worry about: magnesium, phosphate, nitrate, other issues, and I'll touch on those a little bit as well. At the very end, I'm going to go back in with just a couple of slides, talk about what I see as the frontiers of chemistry in reef aquaria. I don't want to say too much about that, but it's the things that I think are most interesting at the moment. So when you're looking at all the things that people worry about in a reef aquarium, definitely calcium and alkalinity are top on the list, and if I can get my pointer to work, there we go. I'll go into these in much more detail, but there are guidelines that people keep at it, and usually it's not too hard to keep these where you want them as long as you have some mechanism for doing that. Then there are particular other things that I think are also very important: the salinity, the temperature, the pH, and then magnesium, phosphate, and ammonia can also be important. These are all the ones that I think are critical. There can be times when something else could be a problem, but I think that most reef aquarists need to at least think about these things in their tank. These are some of the ones that you don't necessarily need to think about if everything's going okay, unless you're really interested in these things. Silica, iodine, nitrate. My pointer's not working again. Okay, we'll do without it. Strontium, redox, boron, iron. Those are all things that can have important applications, but they aren't important for everybody. Thanks. So let's talk a little bit about calcium and alkalinity. Now, the reason we care about these things is because, obviously, corals have calcium carbonate skeletons. And so you need to keep the calcium at a level that's close to what it is in the ocean so the corals can take it up. You also need to have alkalinity that's about what there is in the ocean, or maybe somewhat more. There are reasons why you might want a little bit more. And people often ask, why alkalinity? What is alkalinity? It's this very strange thing that isn't really a chemical in the water at all. And what we really want to know about is bicarbonate, because corals take up bicarbonate. Inside their tissues, they convert it to carbonate, and then they combine it with calcium sort of underneath them and make their calcium carbonate skeleton. Alkalinity turns out to just be an easy way to measure bicarbonate. I'm not going to go into any of the details of alkalinity. I've covered them in some articles, and I can certainly answer questions about it online. But it is just a very easy way to measure something that's very similar to bicarbonate. Now, there's a lot of ways to supplement calcium and alkalinity, and I strongly believe that most reef aquarists would be best off if they used a balanced additive of some sort. And that would be an additive that adds 20 parts per million of calcium for every 1 milliequivalent per liter of alkalinity. That way you're adding things in exactly the same proportion as corals are taking them out, or exactly the same proportion as they are physically precipitating out on heaters and other things like that. So if you add them in that ratio, then they can never get skewed towards too much of one, too little of the other. And for most of the balanced additives, you almost can't add too much in a way that would be harmful. All you're doing is perhaps wasting additives, but you're not necessarily going to harm anything by adding too much in most cases. And the methods you could use this would be lime water, calcium carbonate reactors, the two-part additive systems. You could use the commercial ones, which are very good, or you can make them yourself. All of these are great ways to do it. There are times when particular ones are better than others, and I'm not going to say that one's better than the other. I happen to use lime water, but there are definitely times when the other ones would be preferable. This slide comes from one of my articles comparing these systems, and I just sort of outline here the different costs associated with some of the different methods of supplementing calcium and alkalinity. And I've done it for light loads, medium loads, and heavy loads for a 100-gallon tank. Obviously, the equations are very different if you've got a 5-gallon nano tank. It almost doesn't matter what method you use in an ongoing basis, but the capital costs might be high. So you have to take into account what size system you're going to be supplementing. But for the ongoing costs in Aquaria, lime water and calcium carbonate reactors are really a low-cost way to go. At least they can be. Some of the two-part systems can be more expensive. In the top here, I'm talking about a two-part do-it-yourself system that I will talk a little bit more about later, which you buy bulk chemicals from Home Depot and places like that and make it yourself. But the commercial things like Bionic, there must be half a dozen different brands now, are great two-part additives to use. They end up being a little bit more expensive. If you have a big tank, they can be very expensive. But if you have a small tank, they can be a great way to go. There's also some other nice balanced additive systems that not many people use, but on the next to the bottom line, calcium acetate, that's one of the main ingredients in Salifert all-in-one. And it really is a one part that you can add, and it works quite well. You don't have to worry about mixing two parts. You don't have to worry about adding it slowly or anything like that. But it is expensive. There are also some one-part salt mixtures. I think Tropic Marine's BioCalcium is that way. It's just a mixture of calcium and alkalinity supplements together. It can be expensive too, but for a small tank, it can be an okay way to go. This slide just compares what I think are really the very cheapest ways to go, which would be lime water, calcium carbonate reactors, and the do-it-yourself two-part systems. As you can see, the ongoing costs are really very low for these. For a year, for a medium or heavy load tank, you're still talking $10 to $50 for a year, so it's not really that much for a heavily loaded tank. Okay, but cost aside, there's a lot of other reasons to pick one or the other of different sorts of ways of supplementing calcium and alkalinity. And they each have their quirks, some good things, some bad things. Lime water, for example, you have some limitations on how much you can add because it raises pH, because it's usually done to replace evaporated water. You have some limitations to how much you can put in. But it may have some advantages in that it reduces phosphate potentially. Calcium carbonate reactors are a little more complex, so I sort of think of that as a drawback to them, though that wouldn't inhibit a lot of people. But they also can potentially drive down the pH. That can be a drawback. The two-part systems are really pretty straightforward. They're not complex. They're easy to use. There's no limitations to how much you can put in. You do have to keep track of the salinity, but that's not usually a big deal. Most reef people should be doing that anyway. Other than supplementing calcium and alkalinity, by far the biggest problem people have is how to fix a problem once it goes wrong. And again, if you're using the balanced systems, it won't go wrong nearly as often. My tank using lime water, I don't measure calcium and alkalinity more than once a year probably, because I know it's not skewing very much. I occasionally do water changes, maybe that helps. But there's just not many mechanisms for one to get really high and the other one to get really low. But there are many people who have them get really high or really low for a variety of reasons. The salt mix is off, or they had too much of a buffer because they're trying to solve a pH problem or something. And so I've tried to put together a way that people can solve those problems. And this is a graph of alkalinity and calcium. And, okay, I got a little bit of battery here. So the dot here in the middle represents what seawater would be like. So you have an alkalinity of about 2.5, and you have calcium a little over 400. The red box is sort of my suggestion of where it would be good to keep a reef tank. Now, obviously, I can't claim that it's good to be right here and it's bad to be right there. That would be ridiculous. But this is kind of the area where people should strive to keep their aquaria, I think. But if you're way over here, you need to know how to fix that problem, or way over here. And a lot of people have those problems. And so in the next few slides, which are also reproduced in an article, I'll try to describe how you would solve those problems. If you're up here in this zone, you've got too much of both calcium and alkalinity. So all you really need to do is stop adding it for a while and it'll drift down along these arrows, and eventually you'll move back to where you want to be. That's the easiest problem to solve if you've got it. Down here in this bottom zone, you have too little of both things. So you need to add a balanced additive of some sort and drive yourself up into the red box. That's also fairly easy to solve. But if, for example, you're over here in zone 3, and that would be a case where your calcium is low, but you got plenty of alkalinity. A lot of times people come into my forum and they say, geez, I keep adding more and more carbon dioxide to my reactor, or more and more lime water, and I'm just not solving this problem. The calcium's not going up. It won't. If you tried to start here and add a balanced additive, you're going to move up like this. You move parallel to these lines. So you'd move like this, and you would never be able to move up into this zone by adding a balanced additive from here. So if you're here and you have enough alkalinity and you want to raise calcium and want to move like that, you have to add a pure calcium supplement. So calcium chloride would be what I'd recommend, but there are some other sorts of calcium things you could add. But calcium chloride would be the way to solve that problem most easily. Likewise, if you're down here, you got plenty of calcium, but you've got real low alkalinity. You need to add just an alkalinity supplement. You could go buy baking soda from the grocery store and you could solve this problem. You just add a pure alkalinity supplement and up you'll go. Let me say a couple of words about my recipe for a do-it-yourself two-part system. It's really a three-part system, but I like to call it a two-part because that matches the commercial ones a little better. Part of it is baking soda, and if you want to bake it, you can. I'll describe in a minute what that does for you. The other part is calcium chloride, and I've suggested that folks can use Dow Flake, which is a thing you can buy from Home Depot. You can get a 50-pound bag for $11, at least around here. The folks that live in Florida and other places are not so lucky in that regard. But people use it for de-icing driveways and stuff, so it's a bonus of living in the frozen areas. And then occasionally, the third part would be to add Epsom salts. You can buy those at a drugstore. They're really pretty cheap. And that adds back magnesium primarily. That this system alone really could start to deplete magnesium because you're adding calcium only, and corals are depositing magnesium and calcium together, so eventually your magnesium is going to go down. So that would be the reason to want to add the Epsom salts once in a while. And again, the details of this are in an article that's online. It should be pretty easy to find. The reason you would bake the baking soda, what happens when you start with sodium bicarbonate is you drive off some water, and most importantly, you drive off carbon dioxide. So you end up with sodium carbonate. That also can be purchased directly as washing soda, but washing soda is not a food product, and so you don't have the same assurance that somebody somewhere is watching to make sure it didn't get contaminated with stuff at the plant. So I would recommend that folks use baking soda, just Arm & Hammer stuff. Bake it if you want. Then this additive will have a high pH, and it will raise the pH of your aquarium. It will help solve a low pH problem. If you already have a high pH because you're using lime water and you just want to use a little bit of this two-part additive along with it, don't bother to bake it. Just use the baking soda as is. That'll be fine. The bacon's pretty easy. You just pop it in a regular oven like cookies, and out it comes after a while. It's really not important exactly how long you do it or what temperature. I think this temperature is probably already higher than you need, and it's not critical that it all be forced over to sodium carbonate. It's okay if half of it does. Now, I would be the first to admit that this two-part do-it-yourself system is not as good as the ones you would buy if the ones that you buy are what they claim to be. And I've never tested any of them, so I don't know that they are. But the commercial ones claim that they're not going to skew any of the ions in the water over time. The salinity might go up, but that's easy to change. With this do-it-yourself system, this is the concentration in parts per million in seawater for chloride, sodium, sulfate, magnesium, calcium, potassium. Those are the big ones in the water. If you use this additive system for a year at a pretty high dose, and you're using the Epsom salts as directed in the article, then chloride stays about the same, sodium stays about the same. The sulfate will rise over time because you're adding magnesium sulfate. You've added enough magnesium to keep the magnesium where it needs to be, and you've kept calcium and also potassium where they need to be, but the sulfate has risen, and that is a potential drawback to using this system. It's one of the reasons why I would suggest continuing to do regular water changes with this kind of thing. If you didn't use the Epsom salts, then even though, losing my power again, even though you can keep the sulfate from rising, in fact, you can actually make it go down if you don't add any Epsom salts, magnesium will decline a lot. I personally think that low magnesium is a much bigger problem than high sulfate, and so that's why I've suggested that people add magnesium sulfate to keep the magnesium from dropping. Okay, let me skip to what at certain times of the year is reef keepers' biggest problem, and that is pH. pH is a measure of the acidity of the water, and I would say that the optimal pH is difficult to define. If I really had to say, I'd say it's probably different for every creature in your aquarium, and so you got to sort of come up with some average thing, and personally I think the creatures have probably evolved to be happy in ocean water, so I would aim for what is in ocean water, which I'll come back to in a minute. But if the pH is too low, that can be hard for corals to calcify, and I'll explain in a minute why that is, but basically they need to deposit their skeleton, and as the pH gets lower, it's harder and harder to deposit that skeleton. At high pH, you can get excessive precipitation of calcium carbonate on a heater or on a pump impeller or something like that, so it becomes a maintenance problem. You're wasting calcium and alkalinity. If the pH gets high enough, you can actually limit your ability to maintain normal levels. So as I said, I would personally try to target the ocean pH, which is about 8.2, but people have reef aquariums on a huge range of pH, and good ones seem to be able to range from about 7.8 to 8.6. I don't know that I would want my aquarium right at either of those ends, but the aquariums seem to be fine. But definitely at low pH, that can be difficult to raise. It's not like you can just say, Randy, what do I add to this tank to solve that problem? Well, I can tell you what things you might be able to do, but generally some of these low pH problems can be very difficult to solve, and I'll explain why. High pH is usually not hard to solve. It's usually caused because you're adding something that's a high pH. You're adding lime water, usually. Sometimes the two-part additives can also do it. So if you just add less of those things, you probably would solve your high pH problem. Low pH can be caused by low alkalinity, and I'll show exactly how that works in a minute. But most of the time it's caused by excessive carbon dioxide. It can either be excessive carbon dioxide in the aquarium, or it can be excessive carbon dioxide in the air around the aquarium, which works its way into the aquarium. Either of those two can be the answer, the explanation, and the way you solve them is different. Now, carbon dioxide from the air comes along as a gas, and as soon as it gets in the water, it picks up a water molecule, and it becomes carbonic acid. And the carbonic acid can quickly dissociate into protons, that's acid, and bicarbonate, or two protons and some carbonate. That will definitely happen. So if you have too much carbon dioxide in the air, the pH will be too low because of the acidity that it's creating. This is a graph of alkalinity as a function of pH. I don't have time to go into it, and none of you are probably interested in it, or at least very few of you, but there's an exact mathematical relationship between alkalinity and pH and carbon dioxide. So this line in the middle, this blue line, is if you start with a certain alkalinity in seawater. So let's say you start with natural seawater of alkalinity in the low 2s, and you aerate it perfectly with normal air, you will unquestionably get a pH that's about here, around 8.2. If you put a little more, how do I want to say this? If you change the alkalinity in that water and still equilibrate it with that same air, you will move along this line. And so if you have more alkalinity, the pH will go up. If you have less alkalinity, the pH will go down. So a perfectly aerated tank in aeration with normal outside air would fall somewhere along this line. It couldn't be off of this line. Now, reef aquaria are almost never perfectly equilibrated with the air around them. So many people say, oh, I've got lots of surface agitation, I got all kinds of pumps, I got skimmers, I got all kinds of things. It must be aerated enough, and that's just not true. People are thinking about oxygen. Oxygen is 20-some% of what's in the air. It's easy to equilibrate. Carbon dioxide is only 350 ppm of what's in the air. It's hard to equilibrate. It can take a long time, especially if you're adding things that are sucking up a lot of carbon dioxide. For example, if you add lime water to your tank, that's sucking up carbon dioxide constantly, and you can make the tank deficient in carbon dioxide. So for a given alkalinity of 2, your pH could be very high if it's deficient in carbon dioxide. More frequently, houses have elevated carbon dioxide in them because of all the people inside breathing and exhaling carbon dioxide all the time. The carbon dioxide level can be double or triple or even more what it is outside. So you move from this sort of curve over to this sort of curve, and what you end up with is at a given alkalinity, you are at a much lower pH in the aquarium. And just to reinforce the issue of CO2 a little bit, because so many people think, well, that's just a theory, carbon dioxide, maybe it's something else. It really isn't. It is the answer. It is the only answer. The pH swing that you see in your aquarium every day is only caused by pH, only caused by carbon dioxide. That is the only thing that's changing during the day. It's because your corals and algae and other photosynthetic organisms are using carbon dioxide in photosynthesis to make oxygen and food. And at night, when there's no lights on, your corals and fish and other things are eating this food, consuming it, burning it in oxygen, and making carbon dioxide. So during the day, you're using up carbon dioxide. At night, you are making carbon dioxide. That's why you see a pH swing. If your aquarium was perfectly equilibrated, you wouldn't see any pH swing. So if we go back and look at one of these graphs then, your alkalinity is not changing day to night very much in most cases. So the daily pH swing, you're just moving back and forth along this, using up carbon dioxide, making carbon dioxide. That's what's causing your pH swing. So if you start here with a low pH problem, so your pH is, say, 7.95, you've got normal alkalinity, what can you do to solve this problem? Well, one thing you can do is aerate the water with normal air. If you aerated it with outside air, you would move along this line. You might not get all the way to here, but you'd at least start your way along it, driving out some of that carbon dioxide. But the key is it's got to be normal air. If your house is filled with carbon dioxide already from all the people and pets and gas stoves cooking and stuff like that, no matter how much you aerate it, you might not get rid of the CO2 because you'll just happily stay over here at the starting point. So you can open windows. You can bring air in from the outside with a little pipe coming to your skimmer inlet, something like that. People have been successful with that. But there are perhaps better things, easier things to do. One thing that doesn't work very well most of the time is just to raise the alkalinity. You add a buffer. If you read the supplement manufacturers' things, they say, well, if you add this, it'll keep the pH steady at 8.2 or 8.3. Well, it often doesn't work out because you can raise the alkalinity, and if you don't change the carbon dioxide level in the aquarium, all you'll do is move up this graph. So you can move the pH up a little bit, but you've boosted your alkalinity a lot. And if you wanted to get your pH to 8.2 or 8.3 or 8.4, you might have to move so high in alkalinity, other things just wouldn't be right. So raising alkalinity can help, especially if it's low, if you're down here in the 2s. But if you're already at 3 to 4, maybe higher, raising alkalinity is not going to be the answer. But if you use something like lime water, which both raises the alkalinity and depletes the excess carbon dioxide, you can actually move a long ways in pH. And by far, the people who are most successful in solving low pH problems, it's because they add lime water. A lot of people who have calcium carbonate reactors, they're adding a lot of CO2. They naturally have a low pH in their tank. They drip lime water just for the purpose of raising the pH. They don't actually care whether it's adding calcium or alkalinity, and it may in fact not be adding very much relative to the reactor, but it is depleting the excess carbon dioxide, which goes up. Oop, wrong way. Okay, so as I said, aerating with fresh air can help. One of the ways that you can tell whether you need fresh air is just to take a small sample and aerate it for an hour with just an air stone coming from an air pump inside your house and see if the pH goes up. If that pH doesn't go up, you're not going to help by aerating your tank more. If you do that same experiment outside, the pH should go up. If the pH doesn't go up outside, then you may have a measurement problem of some sort because it really should go up if you're interpreting your low pH correctly. And as I said, high pH alkalinity additives are a good way to raise the pH, especially lime water, because that won't skew the calcium alkalinity balance at all. Shoot, keep pressing the wrong button. High pH, I just want to say a couple words about it. It's an unusual problem, doesn't happen very often. It normally caused by adding too much lime water or maybe too much two-part additive. So if you just use a different additive or use less of it, that will help. If you really like using those, you can add an acid, meaning you could add vinegar, or you could add carbon dioxide directly to the tank. Those solutions all work. Let me say a little bit about magnesium for a minute. Calcium and carbonate are supersaturated in seawater. That's a difficult concept to think about, but there's too much in solution to be stable in the long term, millions of years. But magnesium is one of the reasons why calcium and carbonate can be supersaturated in the short run, and that is because if you start to precipitate a little calcium carbonate onto something, whether it's a particle or if it's a heater or anything, magnesium gets onto the growing calcium carbonate crystal and basically contaminates the crystal. It doesn't want to grow anymore. Once it gets that magnesium on it, it no longer looks like calcium carbonate. So magnesium is very important in allowing seawater to be supersaturated. It's also very important in a reef aquarium, and we are typically in reef aquaria going to supersaturations even higher than the ocean, either because the pH is higher or the alkalinity is higher or something. And if magnesium is too low, you can really be limited in how much you can raise your calcium and alkalinity. Sometimes you can diagnose low magnesium by looking at excessive precipitation on heaters and stuff, but a lot of times it's just because you're unable to maintain the levels that you want. This is just a picture of the relative sizes of various ions. Yeah, question? I wouldn't say that to a chemist, but to a reef keeper, yeah, that would probably be a good thing to say. This slide shows, the only important thing here is it's showing the magnesium content of different corals. And the important thing to see is that the range of magnesium is from a very small portion of the skeleton up to about 4% of the skeleton. And so it's very hard to say how rapidly magnesium is being taken out of your aquarium because it depends on exactly what's in your tank. Certain corals take out very little, some take out a lot. Coral and algae takes out a very large amount. For reasons that are well understood, it's actually not precipitating aragonite, it's precipitating a magnesium calcite. But those will take out magnesium more rapidly. So the amount of magnesium demand in different aquaria varies quite a bit. This slide is just showing the high levels in coral and algae, up to 4% or more of the skeleton. So to avoid the problems that come from low magnesium, I would usually recommend that folks maintain something close to the natural level of magnesium. I don't actually think that magnesium is the cause of as many problems as people attribute to it. I don't think being a little bit low in magnesium is a problem, but some people are very low in magnesium. Some people might only be half of the amount that's in a normal seawater solution. That would be a problem. So I don't think everybody needs to measure magnesium. I hardly ever measure it. But I would measure it if calcium and alkalinity seemed hard to maintain. Now, the seem hard part means you're putting in enough stuff and it's just not going up, or you're getting a lot of excessive precipitation of calcium carbonate on things. If you hardly ever do water changes, that could be an important time to be measuring magnesium, or as the few chemists of you that are out there, you just want to know. I would probably use a commercial supplement for normal magnesium. They're not very expensive and they're pretty easy to use. Okay, let me skip to phosphate for a minute. Phosphate is something that is getting more and more discussion these days as people try to see what happens to their corals as they drive down the nutrient levels to low levels. But I would suggest that people should try to maintain below 0.03 ppm. I know that's tough to do. My aquarium ran for years at 0.1 ppm. But you get more algae at the higher levels of phosphate, and the calcifying corals will grow more slowly. There's no question about it. The phosphate gets onto the growing skeleton just the way magnesium does. Phosphate gets in there, and since at 0.1 ppm you have unusually high phosphate, the corals aren't used to dealing with that much phosphate. It gets onto the skeletons and it's harder for them to grow. There's a lot of ways to reduce phosphate. I've just listed a few of them here. I use the top 3 of those. I grow a lot of macroalgae. You can see a handful of it there. Skimming is a good way. Lime water might be a way. There are also commercial binders that are pretty good at binding phosphate. I don't know of anything at the moment that's wrong with using the iron-based ones, except that they're expensive. And it may be that higher pH actually helps export phosphate from your system. Nitrate is less of a problem than phosphate substantially, but it does encourage algae, and it also, if it's above 0.2 ppm, I think it can inhibit coral growth because the symbiotic algae grow too fast, and they actually take away from the nutrients and other things that the coral host would want to use for itself. And so reducing the nitrate down to more natural levels can really help that. There's a ton of ways to reduce nitrate. I'm not going to go through all these in detail, but obviously reducing food reduces nitrate because all the food you put in ends up over here. That's red. I don't know if you can quite see the red over here, but ends up as nitrate. And if you grow and harvest macroalgae, when the macroalgae is growing, it's taking up a lot of nitrate to be able to grow its tissue. So that's a great way to reduce nitrate. Deep sand beds, a lot of people are really quite negative on them these days, but obviously they can reduce nitrate quite a lot by converting nitrate down to N2, which just bubbles out of the aquarium. The denitrators, the carbon and sulfur ones, are not all that popular, but some people use them. Bacteria take the nitrate, and as they eat organics, they convert it into N2 gas in a carbon denitrator. In a sulfur denitrator, the nitrate is combined with sulfur, so you end up with nitrogen gas and sulfate in solution. A lot of people are afraid of these because they're technologically complex and difficult to control. I've never actually used one, so I can't really comment on them. There's other ways to reduce nitrate, making sure you don't have nitrate in your top-off water. I'll come back to that in a minute. Removing bioballs, has also been quite a lot of discussion about that, but I do think taking them out can be beneficial. And there are various commercial products that can bind some amount of nitrate. I probably, in most cases, wouldn't go this route just because the other ways are fairly straightforward. Let me talk for just a minute about tap water. A lot of people like tap water. And you have to be real careful. If somebody says, I use tap water, it's okay for me, so it should be okay for you. I'm going to explain a couple of reasons why I think that's not true. Even if the person lives next door to you, getting the same water through almost all the same pipes, it's not necessarily going to be okay for you. And one of my biggest concerns with tap water is copper. How much copper is too much? I don't know. That's something we argue about all the time. My aquarium has something like 10 to 15 parts per billion of copper. And it's not coming from the Instant Ocean salt that I use because I can't detect any copper. I can detect down to about 10 ppb, and it's not coming from the Instant Ocean. So it's coming from something else. In my case, I'm sure it's not coming from tap water. It's probably coming from foods and stuff. But at this level of 10 to 15 parts per billion, my aquarium is operating what seems to me to be okay. In some tests that Ron ran, he showed that more than 10 parts per billion copper added to various in natural salt water, for example, decrease the survival of sea urchin larvae. Again, we can argue, well, how relevant is that? How many people are growing sea urchin larvae? And it's a valid question because we don't actually know how much the coral is going to kill something or the copper is going to kill something you do care about. But it does show that copper can be detrimental at fairly low levels, and 100 ppb killed all of the sea urchin larvae in that test. So let's look at what's in tap water. This is our copper measurements that were taken by the utilities that are supplying water to these folks. Here in our hometown of Boston, in the second row, 10% of the homes tested had more than 120 parts per billion of copper. And in the test that they ran, at least one home had 1,100 parts per billion. There's no question that most people would say 1,100 is too much. So some of the people in the Boston area should not use their tap water, there's no question. I think 10% of the people probably have substantially too much copper in their tap water here. But some of them have very low levels. People in Miami seem to be the worst off. 10% of them have 1,100 parts per billion. Turns out that copper comes from your own pipes most of the time. And utilities are trying to do things to reduce copper and lead coming from your own pipes because they can be toxic to people as well. they try to raise the pH of the tap water to reduce corrosion. But people, at least in terms of copper, are less sensitive than our reef invertebrates. And so the EPA will allow up to 1.2 ppm, so 1,200 ppb can be in a lot of people's tap water, and the EPA doesn't care. They say that's fine. That's just not going to be okay for reef aquaria. Nitrate, some water supplies have a lot of nitrate. Most don't. Again, Boston here in the second row has hardly any, not enough to worry about. But people in places like Miami, New York City, 35 ppm, 43 ppm max, that's a lot. That would potentially drive a real algae problem. Phosphate, again, not many water supplies test phosphate, and Boston doesn't have very much. It's pretty much free of that. But again, New York City could have up to 5 parts per million tap water. So if you put in 1% evaporation replacement every day, that's a huge source of phosphate for the aquarium. Silica, again, some people have hardly any. Boston, I believe, actually adds some silica to the water, so that's where it's coming from there. Albuquerque seems to have a huge natural supply of silica, so they potentially have diatom problems there. So for these various reasons, I would suggest that people should avoid tap water. I wouldn't put tap water into an aquarium. All right, let me just touch for a few minutes here at the end on what I think are the frontiers of chemistry in a reef aquarium. There are a lot of things that have been talked about for years and years and years, and there's just no answer for it that I can see. Strontium. Is strontium important? Well, people might say that adding strontium is not important, but that doesn't mean that strontium isn't important. It just means there might be naturally enough in those folks that don't add it. So the question would be, are there some aquaria where the strontium might be unusually low and it would be important? And I think that's an important question. One of the salt manufacturers recently decided they're not going to add strontium anymore because they don't think it's important. Okay, that's a valid thing. I think they should tell folks they're not putting strontium in it, so if people start to see problems, then they might try strontium and see if that solves it. I don't actually know whether strontium is important or not. There's not a lot of good stuff in the literature that says strontium would be important for corals, but there are a lot of aquarists who have added strontium and not done much else and see an improvement. So I think that's an unresolved issue. Iodine, I think, could be an unresolved issue. I don't add any, and I didn't see any change in my aquarium when I stopped adding it, but I don't keep all the organisms that a lot of people keep. There may be some that benefit from it. I tested some things which I thought would be most likely to benefit from it, and that would be the macroalgae that I grow, because those are known to deposit a lot of iodine organic molecules into their bodies. And it didn't help them grow at all. And so I'm not concluding that I need to add iodine, but I don't conclude that nobody should or that it isn't possible that it's beneficial. Trace metals is a real complicated one, and I think it's just totally wide open, partly because people lump them all together. Well, there must be 20 of them. Some don't even have a biological use, so they wouldn't be important, but some of them could well be important. And most importantly, you can't look at the concentration of cobalt or copper or iron or any of those in an aquarium and know whether there's enough or not, because they are so strongly modulated by what they're attached to. The trace metals will be very strongly bound by organics in the water. And I'm going to talk about organics themselves in just a minute. But iron, for example, is totally not available to organisms when it's bound in some organics, like EDTA, and it's readily available when it's bound in other sorts of organics. Well, no test that a hobbyist is going to run or even be able to send his samples out to a lab to do is going to be able to tell you how your iron and cobalt and copper and all those things is bound up and whether it's bioavailable to sea urchin larvae and everything else. So I think it's almost a black hole on trace metals. People can develop additives and they can say, yes, things look better. And that might really be true, but you're going to have to trust the people that are telling you that. And so I think there's a lot of work that could be done on trace metals. Organics, though, is where I see the biggest frontier in reef aquaria. It's also a frontier in the ocean. And an article came out in the magazine Nature just earlier in August that basically said the nature of organics in the ocean is unknown. We've been studying it for years. We haven't made very much progress. And in fact, it's something that I'm going to spend more time trying to understand in our aquarium. Next month's article in Reef Keeping is going to sort of introduce the topic of organics. But for example, most people don't think about this, but the organics in the ocean have typically been there for thousands and thousands of years. What happens is something in the ocean releases an organic molecule, and every bug and bacteria and something else comes along and nibbles away at a little bit of it and changes it, and eventually you get to something that nobody wants to eat, and that's just left in the ocean. And so there are organic molecules that are 10,000 years old that are just floating around there in the ocean, and the only thing that ever gets rid of them are things like gamma rays coming in and ozone reacting with them and stuff like that. They're not biologically available anymore. And how those kinds of things translate into a reef aquarium is really hard to say. But there are a lot of issues with organics. First of all, there's a lot of toxins in our reef tanks. All these things are trying to kill each other all the time. If you look around some of your corals, you see areas around them where everything's dead because the sweeper tentacles have killed them. Sometimes because they've stung it directly, sometimes because they're releasing things into the water nearby. So toxins is a big concern, and obviously it's an even bigger concern with some larger organisms that if they die, the tank gets a wipeout. That too can relate to toxins. Organics are starting to get a lot more notice as a nutrient source. People test for nitrate, ammonia, stuff like that, but rarely do people test for the organic nutrients that are in the water, and that can be a driver for algae. It can be an inhibitor for coral growth. Along those lines, calcification inhibitors, there are definitely organic molecules that arise naturally in reef tanks that will inhibit the growth of your corals. So skimming and carbon and those sorts of things that remove those can be really beneficial. Everybody knows the issues with yellowed water. A lot of organic molecules are colored, and they could build up in an aquarium if you don't export them adequately. I would say that yellowed water is something that people can look at their tank and say it's yellow or not. You can't look at it and say, geez, do I have toxins in there or not? That's a lot harder to know. You can look at your tank and say, hey, it's great, I'm happy with it, but you can't look at it and say, I'm sure it wouldn't be any better if I took out those toxins. And as I mentioned a little bit earlier, the bioavailability of the metals, I think that is a real tricky one. We've had a lot of online debates about how you can tell whether any of these things are bioavailable, and I think you really can't. So it becomes a problem for us to investigate as we go forward. Let me just show, in closing here, some structures of the toxins that are known to come from various organisms. I just happen to have these because I'm writing an article on them now, but this is a toxin that is present in algae. It's released into the water. So if you have red tides and stuff, this is one of the toxins that can be in it. This is tetrodotoxin. It's a little bit more complicated of a molecule. It's still something that's tractable, and organic chemists would understand that fairly readily. But some of them can be huge and complicated, very complicated toxins. This one comes from dinoflagellates, and it's a very complicated molecule. It would take chemists many years to synthesize this from scratch. And so there are things in the tank that we should recognize are complicated. They're not as simple as calcium and magnesium. There could be thousands of these in your water at different concentrations. Most are probably too low to be important. Some may be high enough that they're irritating something somewhere in the water. And it's just something that I think we'll need to think about going forward. And that's it. Thanks very much. Questions? I'm also happy to entertain questions afterwards if people just want to come up afterwards. Yeah. I think, I don't know if Habib is here, but that would be a good question to ask. He's the owner of Salifert, and he could explain that. But it turns out that in normal seawater, at least, bicarbonate is about 80 or 90% of the alkalinity. So if you measure alkalinity, it's a pretty good measure of bicarbonate. I do think that people who start to want to automate their system might end up with some kind of automated electrode for measuring bicarbonate, and they may have to sort of adjust their thinking from alkalinity to bicarbonate. But I think it's a practical issue of how do you measure bicarbonate.
Hey, Randy, if you could get everybody, or if you could repeat the question.
Okay.
If they don't go up to the microphone.
Okay. So that last question was, why do we measure alkalinity instead of bicarbonate directly, if that's what we care about? Yes, question. I think that the question is, what do I think of the combination of lime water and a calcium reactor? I think it's a great combination. It takes the best of both of those things, and the calcium carbonate reactors are great, except they deliver too much carbon dioxide to the water and lower the pH. Lime water does exactly the opposite. It sucks up the carbon dioxide and raises the pH. So together, you can get a great system that doesn't have pH at the extremes. Any more questions? Yeah.
Well, that's a very good point you brought up about your CO2 level in the house. If you have a high bioload of people and or pests, and you don't open your windows, it's a major problem. I have that problem at home. I also have well water, which is high in CO2.
Yep.
So I have to aerate that and have to add a lot of buffers. I have to try adding lime water.
Yep, the pH issue from carbon dioxide in the house also is seasonal because people open their windows in the spring and the fall, but at least in some places they close them in the summer to air condition. And so I see the questions on pH in the chemistry forum that go up in midsummer and then they go down in the fall and then they go up in the winter again when people close up their houses to heat. So it really can be solved by opening windows too, but not everybody wants to do that when it's snowing outside. Question in the back.
You mentioned some of the biomolecules that get
Yeah.
trapped in there that can't be harnessed by any of the organisms. I'm
Yeah.
also concerned with things in the human environment like hairsprays and various
Absolutely,
deodorants.
absolutely. A lot of those would go into the tank very readily. The question was about things in the house, organic molecules in particular going into the tank. Hairsprays is one issue. Pesticides is a big one. People get rid of their cockroaches or fleas or something, you can do big damage to your tank. I actually had a nest of bees in the side of my house a few years ago, and the contractors didn't bother to ask me. They just sprayed it with something, and all of a sudden, the only thing affected in the tank were a bunch of limpets, but all the limpets were laying on their back upside down. So definitely things in the air can get into the tank, and a skimmer and carbon can at least be some help against those kinds of things, but not necessarily going to preclude the problem. Yeah, question?
Can you explain the difference or the value of an RO unit versus an RO unit?
Yeah. Most cases, an RO, the question is the difference between RO and RODI and the value. An RO unit will take out almost everything you're worried about to some extent. It should take out at least 90% of most things that you're worried about. If you happen to be one of those places where you have 1,200 parts per million copper, I wouldn't rely on just an RO to solve it, but you're not going to know that you're one of those houses. Most people are going to be okay with an RO, but if you start at 1,200 ppm and you take out 95% of the copper, you still may have too much. And so I use a DI. The other thing is, here in Boston, we have chloramine in the water. And I noticed that when my DI things are shot, the water coming out of the RO stinks like crazy of ammonia because the RO breaks the chloramine into chloride and ammonia, and the ammonia just happily goes through if there's no DI there, and you get a lot of ammonia in the water. That isn't necessarily a big problem if you're just adding dribs and drabs of it because it's probably pretty low concentration once it's in the big tank. But if you were to do a 10%, 20% water change with something with a lot of ammonia in it, that could be a big problem too. Question? Yeah. No, it might be, but there really isn't very much solids in it. You can only dissolve about a couple of teaspoons in a gallon. And so you're much better off buying solid lime or solid calcium hydroxide. It's often sold as something called kalkwasser, but that's not what it is. It's the solid that you use to make the kalk. It's sort of like buying fruit punch, but you buy the dry mix and then you mix it with water, and people would still call it fruit punch, I guess, even when it's dry. Any other questions? Yeah.
Well, one last thing you didn't mention, if you have well water and you run through your RO system, you still need to degas before you run.
Yeah, carbon dioxide would not come out in an RO. That's right. Carbon dioxide would go right through an RO. It would get stuck on the DI, and it would kill your DI real fast. Yeah, that can be an expensive problem, and it's expensive to solve too. De-aerating or aerating the water to get rid of the CO2 can be expensive itself. Mm-hmm. Yep. The DI will solve the problem, but it'll be expensive. Any other questions? Yeah, in the back.
Is there a role for, I've seen several manufacturers sell amino acid.
Good question. I forgot to mention that on the organics. Absolutely. I think there is real potential there for amino acid supplements or food supplements that contain amino acids to be very valuable. It's thought that some amino acids are critical for calcification. They actually control how corals, they make proteins out of them, but those proteins control how calcium carbonate grows into the different shapes and patterns that it does. And seawater is thought by some people to be deficient in some of those amino acids that these corals need, and some of them do take it directly out of the water. So there could well be substantial benefit from things like Salford's amino acid supplement. I haven't personally tested any of them to say. A few people that I've talked to have had sort of mixed results with them, but I think that is one of the areas where there really could be substantial benefit. Greg? I think for the chemists, I think they're the ones with carboxylic acids on them that aren't on the amino part. So things like aspartic acid, that sort of thing, because that carboxylic acid is what's used to anchor to the calcium carbonate as it's growing. There are several of them in the literature. Aspartic acid is one of the big ones. Yes?
Towards the end of your talk, you mentioned toxins that corals can give off, and in answering this gentleman's question, you suggested carbon.
Yeah.
I'm curious what your suggestion is about how much carbon to add and how often.
That's a good question, and I'd have to say that I'm negligent in that I don't use carbon very often, and I don't actually see why I shouldn't, except that I'm lazy. But so I don't have a good answer for how much carbon. More than I use, which is not very much, but sorry, I can't really say. Probably not quite as much as the carbon manufacturers would recommend because they're trying to sell it. But other than that, I would go by what you hear other folks using and are happy with. Any's better than none. I would change it fairly frequently. I would take it out after a couple weeks because I don't think it's probably doing very much after a couple weeks. I think the active surfaces on the carbon are going to suck onto something pretty fast. And then if you leave it in longer, it's not doing very much. Yeah, question?
Ozone is a way to burn up organics, right? So is that a way to get rid of some of these toxins?
Yeah, ozone is a double-edged sword. I haven't been a fan of ozone in the past, but it would be a way to decrease toxins. It would be a way to get rid of organics that were building up in the water that weren't being taken out. I personally have a different viewpoint on how those organics actually end up being taken out. I don't think, for example, that ozone directly impacts skimming. I think ozone tears into molecules that then bacteria can happily eat those molecules that they weren't able to eat before, and then the byproducts of that bacterial growth are skimmed out. But however it happens doesn't really matter. Ozone could be beneficial, and as we learn more about organics, I might change my view on ozone and suggest people use it more. At the moment, I just mostly don't recommend it because people might use it in ways that aren't beneficial, but I think it could be useful. Yeah.
To follow up on this, water changes are primarily useful. I mean, if you got good chemistry, water changes are primarily useful for toxin removal.
I mostly suggest that folks do water changes to take out things that are getting in that you can't otherwise take out very easily, like the copper that's coming in with foods and your reactors and stuff like that, as opposed to trying to reduce nitrate or phosphate or something like that, which I don't think water changes can really keep up with or do a very useful job for. So I do encourage people to do water changes. In fact, I bought one of those dual head reef filler pumps so I can just throw a switch and it slowly over a period of a day changes 20% of the water and I don't have to do anything. And I, like carbon, I was very negligent in doing water changes till I set up an easy way of doing that. I do think water changes are beneficial, and if we have confidence that the artificial salts or natural seawater that we're using are good, then there's really no reason to not do them other than cost, perhaps. That's hard to say, but 25% a month, 20% a month. I think if you can afford it, and you're doing it slowly so that things aren't getting a jolt of something that's very different than what they're used to, then you can change a lot more and it's probably beneficial. But it's very hard for anybody to say, what is the limiting thing that's harming your tank? Is it because you have too much copper, too much nitrate? I would say that the one thing that I think about fish that a lot of people worry about is I don't worry about fish and nitrite. I don't think that seawater fish are affected by nitrite at any of the levels that we would have in a reef tank. So I personally don't think people even need to bother to measure it. But other than that, I don't have anything to say about fish, really. I think they're less susceptible to a lot of the unusual problems than the host of other inverts in the tank might be. Yeah, question?
You're using a calcluster with the calcium reactor. How much and how often would you get? I would have the lime water replacing, personally, the way I do it is I have the lime water replacing all of the evaporated water. And I would just add different amounts of solid into that liquid depending on how big of a pH effect you found you needed. So I would just add more and more and more until you were happy. And if you still weren't happy when it was saturated, then, well, you live with it. But I would replace all the evaporated water, and I would suggest doing that drip-wise. I actually use a pump, so I make up 44 gallons at a time and let it pump that in over 3 weeks or so. So it's really not very much effort on my part. People say, lime water, I don't like all the work, but that's because they're mixing it up every day and they're shaking it and settling it and sitting it up on top of their thing. And that's an okay way to do it, but it's labor intensive. And you can deliver it from a big reservoir, assuming you have a basement or someplace to put that, without any problem. Question?
Is it also impacted by CO2 though, right?
It is, but a big trash can with a lid on it is plenty stable for that period of time. Carbon dioxide does get in. It does make a skim coating of calcium carbonate on the surface. But people have worried too much about it depleting the whole thing. And I've measured it and I actually have an article that shows the concentration of lime in the water really doesn't go down very much. If you stir it or if you bubble into it, absolutely that would be bad. But if you just make a big still container of it, it'll be fine. Question?
About using the ozone, the reservations, other than rating your ORP too high, what were the other ones?
My concerns with ozone are that you generate reactive oxidized species like bromate or something like that would then escape from your reactor, wouldn't get onto whatever carbon is taken out the ozone, and would go and irritate things elsewhere in the system. That is more my fear of something that could happen rather than evidence that it does happen. Certainly those things form, but how harmful they are to the rest of the tank, I don't really know, so I just try to avoid it. Question?
You said one of the sulfate factors could add strontium?
Yeah, Oceanic doesn't put strontium or boron into their salt mix because they don't think we need it. The thing that concerns me is I don't know what else they've left out because they don't think we need it. So personally, I would rather them make it look just like natural salt water, and then if I wanted something else in it, I would add it. If I didn't want that in it, well, I could kind of be stuck. But yeah.
On your three-part solution, when you add the Epsom salt,
Yeah.
would there be any benefit or recommendation for your dripping lime water and you're running a calcium reactor? Do you still want to do the Epsom salt occasionally?
No. That's a good question. The reason the Epsom salt works out okay with the do-it-yourself two-part is because there's so much chloride coming in with the calcium chloride that by itself that will raise chloride relative to sulfate over time. If you're not doing that, but you're doing a calcium carbonate reactor or you're doing lime water, you're not delivering all that chloride. So the extra magnesium sulfate you add to boost magnesium is boosting sulfate a lot relative to chloride because you don't have any other source of chloride coming in. So that's why I said that I would recommend a commercial magnesium supplement, which would be balanced between chloride and sulfate. And it turns out they're really not very expensive. I actually started to go down the path of saying, I'm going to invent a cheap, do-it-yourself magnesium additive, and it turned out that it was really pretty cheap to begin with from ESV or something like that, because you don't use that much. Whereas calcium supplements, you use a lot. You use it every day. But magnesium supplements, you might only use once a year. It doesn't end up being a very big cost. Question?
Is there any difference between the magnesium sulfate and magnesium sulfide as far as?
Yeah, I definitely wouldn't use sulfite. Magnesium sulfate is Epsom salt. Sulfate is the second most prominent anion in seawater. There's almost no sulfite, and it would be a reactive, I think, an ore-producing thing. I wouldn't add it, probably. Yeah.
In your concern for ozone and focus on redox potentials, what's your opinion on being concerned about?
I repeat question, sorry. The question was, what are the concerns of ORP relative to ozone and what are my feelings on it. I don't think that ORP itself is a good parameter to judge by. I think ORP might be an okay way, if you're doing it properly, to judge how the aquarium is operating in the absence of an additive. But once you start adding an oxidizer, I'm not sure that raising the ORP that way is at all equivalent to raising ORP in other ways. And it seems very artificial to me that you've added an oxidizer, so you've skewed the tank toward oxidizing species, but you haven't necessarily gotten rid of the things that were driving ORP down to begin with. And I don't think ORP is the actual endpoint that anything cares about. I think it's the things in solution that are all around them they care about. And if there's a lot of highly oxidizing things and a lot of highly reducing things, that's not the same as if the water were balanced out at something in the middle. So in general, I'm not a fan of even measuring ORP, and even though I have the electrodes at home, I don't even measure it on my tank, because I don't know what I would do with the numbers if I had them. But I'm not a fan of saying an aquarium with an ORP of 400 is necessarily better than 300, and so you should drive it up to 400 with an oxidizer. If you drive it from 300 to 400 because you are using carbon to take out organics, or you're skimming, or you're aerating, or something that otherwise seems like a good idea, then I think it's a great thing to do. But don't take my personal bias against ozone too strongly, because I know a lot of people do it and they do it just fine. It's just not something that I'm as comfortable with as other ways of monitoring a tank. Yeah.
ORP seems to mirror pH.
Yes, absolutely.
So I've heard people say, it's just really kind of an inverse measure of pH.
ORP does track very closely with pH because it's kind of a complicated thing, and then there's an article online that I wrote that shows that tracking from some people that supplied me with some data, and I show the theoretical reasons for it. There is an exact theoretical reason why it should track with it, but you can still, even though you're tracking with pH, you can be tracking it real low or you can be tracking it real high. So it's not just a pH fluctuation, but it certainly is, and if somebody tells you, I have an ORP of 300, you have to say, well, did you calibrate? What was the pH when you measured it? What time of day was that? All those kinds of questions for it to really mean anything. And I actually think that most people don't calibrate ORP properly, and so the numbers are really pretty vague. Yes? Definitely. The Red Sea not only has higher salinity, but it has somewhat different ratios of ions in it. I think there isn't very much difference in the major ions between like the Atlantic and the Pacific, but there certainly can be local differences. I don't think any of those differences other than salinity are probably things that most reef keepers need to alter in their aquaria, probably because the differences are within the natural differences and the uncertainty of test kits and all that kind of stuff. Yeah. The question is whether rapidly dropping phosphate levels is any concern. I don't know. I can imagine a reason why it would be, especially if the symbiotic algae in corals were suddenly a lot less happy and they needed to be ejected or something. I haven't heard of that many people that had a problem. I have heard of people that have funny changes when they start to use the iron compounds, things like alkalinity changes. I still haven't figured out how any of those things actually happen. So it might be a concern, but I don't know that it is. Yeah, that's possible. I mean, there are a lot of things you could imagine happening, especially with pH. A number of people say they see alkalinity depletion. I haven't yet understood that. A lot of people also see the iron oxide things cementing to each other with calcium carbonate in between. And even though we've talked a lot about it in the chemistry forum, I haven't come up with an explanation of why that would be happening, except that phosphate and organics, like magnesium, get onto the surface of growing calcium carbonate things and prevent the growth. They contaminate the crystal. If you take all those out of solution, you may suddenly find yourself supersaturated relative to what's in there. So right downstream from one of those particles, maybe you're too supersaturated and you get precipitation. I don't know if that's the explanation or not. It's the only thing I can think of. But certainly if you change the phosphate levels a lot of organisms might suddenly find themselves too big for their own good, unable to get enough nutrients. They may start to die. All kinds of stuff could happen. They certainly might not photosynthesize as much if there's not as much of them there. Yeah. Yes?
You talked a lot about measurement. You want to give some advice about cost versus ease versus various ways to go?
Measurement of, the question was cost versus ease of testing. Is there a particular thing? Or I think there's a number of test kits that are good enough. I think we are lucky as reef keepers that we don't have to keep things real tight. I think calcium can range a lot without being a big problem. I think alkalinity can range a lot as long as it doesn't get too low and not be a problem. So I think there are a number of test kits available, the Salford kits, the Hatch kits. Lamont makes some good kits. There certainly are others. And I just think we're real lucky that we don't need a real precise measurement. So the difference between 400 and 420 parts per million, maybe some of you would do something. I wouldn't do anything about that sort of difference. If my tank were 350 or 300 parts per million calcium, yeah, I'd do something. Any questions? Yeah.
Does the RO DI filter take out the magnesium from?
Yes, absolutely. It takes out magnesium. The DI will take it out, and so will the RO. So a DI alone would also take it out. Anything else? Okay, thanks. If you have any other questions, I'm happy to answer online.